Hello everyone, welcome back. So today we're going to take a look at a super interesting topic, which is Verlet integration. This has everything to do with physics simulation using a digital machine, using your computer. And in our case, we're going to take a look at Verlet integration in the context of game development, right? Game programming, which is what we mostly study in our channel here. Look, whenever we talk about Verlet integration, you will see people talk about numerical integrators, which is a very scary name for something that is actually not that hard to understand. And we're going to understand a couple of numerical integrators today, but we will focus on one called Verlet, or Verlet integration, right? If you are from that region of France, otherwise it's just bubbly simulation, right? So Verlet integration is going to help us simulate physics movement in our games, right? So I want to start, let's just go back to the basics and look at this example right here. Think about an object that is under constant acceleration. And I think the simplest case will be an apple that is falling due to the weight force, right? So there is this weight vector pulling that apple down, and the apple falls under a constant acceleration. The velocity increases as time passes, and that apple falls down. And look, I know that if you had to simulate this in your machine, you probably wouldn't even have to do any fancy physics simulation. You would just go and increase, right? Every frame of animation, you just increase the velocity, and you will see this displacement of position of that apple going from top to bottom. But I wanted to think a little bit different, because we're going to have several different forces being applied in our objects, right? Let's say, for example, that you have the wind force as well, right? Not only gravity, not only the weight force, you have wind blowing this way, you have wind blowing that way, so you have these different force vectors also being applied horizontally. They are all going to be dynamic, right? All these forces applied in our object. So the apple is going to fall down, it's going to have this weird movement. It is dynamic. We have several different things applying forces at different animation frames of our game, right? So animation frame per animation frame, we're going to have different forces acting. So it is a dynamic system, right? So things get a little bit more challenging for our simulation, right? It's not just simply having an apple falling down. Now you have these different forces being applied, and you have to respond to that simulation. You have to change the position of the apple dynamically as those forces, as those accelerations and velocities are being applied and changing dynamically frame per frame. All good? So I want us to pause, and I want us to go back to whenever we were learning about constant acceleration in high school, right? Or elementary school, high school, you name it. So think about this. We learned that we have this graph of position through time, right? And time is our independent variable. Time grows as we go here to the right. And this thing right here is a function from reals to reals, right? So real numbers mapped into real numbers. This is a function from the real numbers to the real numbers. This thing right here is what happens to the position as time passes, right? Object under constant acceleration. This is our apple falling down, right? And we can even expand, and you probably remember that we have the position x, right? And I'm calling x, this position x of the apple is going to be the initial position x0 plus the initial velocity times the time plus half of the acceleration times the time squared. You probably know this thing by heart. This is the analytical equation that will give us the exact position of the apple in a certain time that we want, given that this apple is under constant acceleration, which is the case because the apple is falling, right? Gravity, the velocity increases at a constant rate of change, acceleration going down. Right. But this is all good. This is real numbers. This is continuous, right? This is a continuous function. It doesn't matter how much we zoom in, there are no holes in this function. There are no holes in the real number line. But this is not what we are dealing with a computer, right? A computer does not have these ideas of infinity, this continuous. Everything is discrete. Everything in a computer happens at this discrete time interval, right? You have this tick, tick, tick of this computer clock. Your CPU ticks everything, right? Tick, tick, tick. You have a certain frequency of that clock. You have 4 gigahertz in your processor. You have 8 gigahertz, you name it, right? I don't know. Back then, we had 1 megahertz to simulate this type of things, right? Back whenever we were retro computing and things like that. But you have a discrete number of time intervals. So we do not handle continuous functions with a computer. There's no idea of continuous simulation of movement. We have to calculate everything discrete time intervals, time step per time step. This is where we're going to have these ideas of these numerical methods. Or in our case, you'll see people call this also numerical integration, right? Because we are trying to integrate that function. We are trying to find out what is the area under the curve, right? We are wanting to find out, in the case of the position through time, we want to find the velocity, right? How much that velocity changes so we can go and update the position in the next frame. Right, so look here, instead of having this continuous function, right, this is our previous exact function. This does not exist in the computer. What exists in the computer is all these discrete times, t0, t1, t2, t3, t4. This is how many frames per second. You can think of it as frames per second, right? So simulation step by simulation step in your computer, we have these discrete time intervals. And what we have to do is, at discrete time intervals, we have to go and try to find what is that exact solution that our constant acceleration is giving us, right? So as you can see right here, as we are dealing with these discrete intervals, the estimation is never perfect, right? Because depending on the time that we have from the previous frame to the next frame, and then this frame to the next frame, we have this gap right here. We have this delta time, this difference of time between one frame and the previous one. The bigger this difference of time, the bigger is this interval between one time and the other, the worse is going to be our estimation of where those values are going to be in our constant acceleration function, right? It doesn't have to be constant acceleration. This can be any function, right? I'm trying to estimate discretely. I have to go and use a numerical method to go and try to estimate the position at these discrete time intervals and try to find something that fits that curve. Look at this example right here. This thing right here is one numerical integration method that we at each time step, we look at the slope, we look at the velocity of that curve, and we try to estimate the next position based on that slope, based on that tangent value. Right, so this tangent value, this slope, if you ever studied calculus before, this tangent, this slope, this rate of change is what we call the derivative of that function, right? So we have to go and differentiate to find that slope at each one of these positions. A computer cannot solve those functions, those analytical functions, that continuous thing. It has to use a numerical method to go and start predicting, right? Looking at this value, trying to predict where the next frame is going to be, right? The position. And then as we are here, we're going to look and try to estimate the next method. Do you see how estimating, this idea of finding this approximation, is not perfect? We're going to have this approximation errors, right? Because as we are trying to approximate, we can only see from one time step to the other. So if we find the slope at this point, the prediction is going to be a little bit off. And then this one is going to be a little bit off, even more off, even more off. So we have these approximation errors. This is something completely normal in a numerical integration method. We have to deal with these ideas of accuracy, stability. So we have to find different integration methods. And here is where this thing's called Verlet Integration comes to play. Verlet Integration is one numerical method, is one numerical integration that tries to play with these ideas of predicting the position of our object in the next frame, given that we are in this current frame. It's all about estimation, prediction. How do I predict where is going to be my next position of that object, given that I have this velocity, given that I have this position right now in this frame? Where does my simulation estimates, predicts that the next position is going to be? Right? So speaking of numerical integration methods, the simplest integration method, I would say, that is something called Euler Integration Method. Right? So Euler method, as you can see right here, is exactly what I said before. At each time step that you have, we look at each one of these positions and we try to go and look for the velocity. So we look at the rate of change of the position, which is the velocity, which is the slope of our function, right? So what is the slope at this movement right here? This position right here, at this time interval, the slope is like this. So this is what we're going to use, that slope we're going to use to predict the next position. As you can see, it is not perfectly accurate, but this is what Euler method gives us, right? So the Euler method, if you want to look at the rigorous formula that explains it, is we're going to have this x of n plus 1, x of n. So x of n plus 1 is the next position in time, right? The position of the next frame, if you want to think like that. So the next position of the next frame is going to be the position of this frame, right? X of n, plus the velocity of this frame times delta time. What is this scaled by delta time? Delta time is the distance, right? How long it took from one frame to the next. What is this difference of time, this delta time? Delta time means how long we have to wait, how much time elapsed since this frame and the previous one, and then the next one and the next one. This difference of time is the delta time. So this is how we go and we try to estimate. We look at the velocity, which is the rate of change, which is the slope, the tangent. This thing right here multiplied, scaled by the delta time, so it is the previous position plus this slope scaled by delta time is going to give us the next position in time. And this is exactly what we're going to achieve with this Euler integration method. Does that make sense? This is Euler method, is one of the simplest one. We just look at the slope and we multiply with scale by delta time, which is the time difference. And the velocity of the next moment in time, right? So the next velocity, we need to update the next velocity, is going to be the velocity now plus the acceleration of our system, right? The sum of all the forces are going to give us an acceleration. And then we also multiply by delta time. So it's all about updating the position and then updating the velocity so we have a new position in the next frame. We update the position, update the velocity, and then the position, the next one is going to use the new velocity, update the velocity again, update the position, update the velocity, update the position, update the velocity. And everything is given by the acceleration, right? In our case, our acceleration was constant, but you can have these dynamic forces acting, right? You can have, remember, the fan blowing wind, you can have friction, you can have a damp, you can have all these different forces acting. And forces being applied on our objects, they are going to result in an acceleration. Remember, force equals mass times acceleration. Acceleration, if we look at the masses and if we look at the forces, this is what gives us the acceleration of the system at frame per frame, simulation step by simulation step. Okay, so this is Euler method. If you want to code or implement Euler integration, it's pretty simple, right? You can have, let's say, a class point, and in our constructor, you see how we have position, velocity, and mass. This is what we store. We store the position and the velocity per particle, per point. And in our update method, right, we have this delta time, which is how much time elapsed since this frame and the previous one. So we have this time difference. We pass delta time as a parameter here in this function. And then, do you see how we are computing this acceleration value based on the sum of forces of the system? So this sum of forces is going to be dynamic. We're going to have wind, gravity, weight, friction, all those force vectors applying. We have the sum, the resulting force, and then we divide by the mass. This is acceleration, right? Remember, acceleration is force divided by mass. F equals ma. This is how we get the acceleration frame per frame. Now that we have the acceleration, what do we do? Well, I use that integration method. I say that the position, right, this position is going to add the previous position plus the velocity scaled by delta time. The velocity is the one given by, and this dot velocity, the velocity of the next frame, is going to be the old velocity plus the acceleration times delta time. Look at this code and see if you understand what is going on. We are updating the position, and then we are already updating the velocity that is going to be applied on the next frame. Update the position, right? So new frame, position updates, velocity adds, so we use this velocity on the next frame to update the position above. Velocity, this line right here is us integrating the velocity to find the new position, and this second line is us integrating the acceleration to find the new velocity. This is what we call explicit Euler integration method, right? It's one of the simplest integration methods. We just look at the velocity, we find that slope, that rate of change, and we scale by delta time to estimate the next position, right? And then we find the new acceleration based on the forces, we integrate again the position and integrate the acceleration to find the new velocity of the next frame. And then the next frame we update position, update velocity. All good? This is what we call the Euler method. And you know what? Let's go ahead, and I want to see this in action. So I have here in our P5.js JavaScript editor, I have a very basic skeleton of an application that displays 2 points, right? These 2 particles right here. So I have a constant screen width and screen height, which is the inner width and inner height, so it's the entire canvas width and height. And then I have a class point. It can be point, it can be particle, you can name it whatever you want. Our constructor, we pass the x and the y position and the x and the y of the velocity and the mass, right? Because we need to break these things down into 2 components, right? X and y. They are vectors, right? Both position and velocity are vectors. And then I initialize the position x and y, initialize velocity x and y, and I initialize the mass. And then we're going to have this update function right here, which is super important, which we're going to do very soon. And the render of each point, I can just fill a little circle at that x and y position, which is what you see right here. Given that I have this class point, I can now create several different points. I have an array of points where I create points at certain x and y positions. I'm just giving the mass 1.0 for both of them. These are the 2 points that you see right here. So function setup, here is where I create my canvas at that width and that height. And in my function draw, this is super important. This function draw is the function that is being called frame per frame, right? So every frame of animation of this JavaScript app here, we're going to clean the background and we're going to render all the points. So for all the points of that vector, I'm going to ask for point.render. And this is exactly what you can see right here. So far, there is no movement, right? Because I do not have anything being applied. There is no gravity, weight, force, there's no wind, there's nothing being applied. So we are going to change that. We are going to have, let's just say force x, which is 0.0, and force y. Let's say that we have 300 force y. And this force value right now, it is basically a constant. We are not going to change the force as the frames progress, but you get the idea, right? You could have different forces being applied. If you press a key to the left, key to the right, you can have wind force, so it could be dynamic. I'm not going to make this dynamic. It's going to be just a constant acceleration going down, almost like the force of gravity. So now that we have force x and force y, in our update of each particle at each point, we need to calculate the acceleration, x and y. And we know the acceleration comes from that F equals ma formula, right? So the acceleration is equal to the force divided by the mass, which means that it is the force x divided by this dot mass, right? The mass of this point, and almost the same thing, but now acceleration y. So the 2 components, x and y. This is us finding the acceleration. What does the Euler integration method, this explicit Euler integration method, tell us? The position x comes from the old position x plus equals the velocity scaled by delta time. Okay, but where is this delta time coming from? Well, delta time, we need to pass as a parameter here. Before we render all the points, we need to, for all the points, we need to say point.update passing the delta time. But there is just one thing here. There is this thing called delta time in the P5.js framework, which gives us in milliseconds how long since the last frame was updated. So what I have to do here is, let's just create something called dt for delta time, but I want this value to be in seconds, right? So it's going to be delta time, which is in milliseconds, divided by 1000 to give us this value in seconds. And let me just add this comment right here. And this one, we update all the points, all the particles, using the Euler integration method, right? This has nothing to do with Verlet yet. This is Euler integration. The Verlet integration is based on this thing right here. We're going to build on this knowledge that we are acquiring here. So this was this.x, and the y is the same thing. We just add to this velocity y, scale by delta time. Beautiful. So we just estimated the position of the next moment in time, but we are still missing the integration of the acceleration to find the new velocity of the next frame. So this dot velocity x, we need to add to the acceleration times delta time, right? We need to integrate the acceleration, which is acceleration that we calculated above, scale by delta time. This is us integrating the acceleration to find the new velocity, x and y. This thing right here is what we call explicit Euler integration method. By updating the position and updating the velocity frame per frame, we're going to achieve this constant acceleration based on the forces that we are applying on the system. In our case, it's just a constant force. Let's see. Well, nothing happened. Maybe I forgot something. I have to pass this delta time as a parameter here in our update. There you go. So do you see? We start at this zero velocity and we increase at this constant acceleration going down. This is us simulating movement in our scene. Let me just pause right here and let's just force these objects to always stay inside the canvas, right? So let's just bounce back up, bounce from the left, bounce from the right. We have to just constrain these points to be always inside the canvas. And I'm going to save us a little bit of time, and I'm going to come here in our point, and I'm going to add a new function called constraint. It's going to constrain that point inside the canvas width and height, which is basically bouncing off the walls by flipping the velocity. So if we reach the left part, I'm going to force the x position to be on the exact top of the left wall, and then the velocity x is flipped by -1. So if it was negative, it becomes positive, and the same way, else if the x reaches the screen width, which is this border right here on the right, if we reach the screen width, I'm going to force the x to be exactly on the screen width and flip the velocity -1 again, just flipping that thing from positive to negative. And you guessed it, so if the y is less than 0, if we reach the top, we go and we flip the y velocity to go now positive, and if we reach the screen height, the bottom of the screen, we flip the velocity y -1. This thing right here, let me just show you what happens. In this scenario, using the Euler method, the Euler integrator, we have the position and the velocity vector, and when we estimate, and then we have a wall right here. Eventually, if we go and we estimate the new position, we look at the velocity, we estimate the new position, and we look at the velocity, eventually we're going to penetrate that wall, right? So we're going to find a collision. It's going to be bigger than the screen width. If this happens, you see how we have these discrete time steps right here? I am forcing the x to go exactly right here. We're going to use what we call the projection method to go and project and force the position to be on that wall. Right? We just go and we move to make sure that we don't have any displacement. We just force to be on the wall. And then we go and we flip the x velocity to go in now negative. And then we just flip this velocity to go negative. Do you see? Now we are on the correct path again. The velocity is negative, we flip that velocity, we force that x to be right on the wall width, and then we flip the velocity. Now we are on the correct path to continue our simulation. And then eventually we're going to bounce on the left, bounce on top, and then the exact same thing happens. This thing right here is what we call the projection method, just forcing our ball to come here and be projected in this normal plane of the wall. Right? This is what that line of code is doing whenever we were forcing this.x equals screen width, this.x equals 0. This is us kind of simulating the projection method, and then of course flipping the velocity x, flipping the velocity y. This is us bouncing against the walls of our canvas. which will give us exactly the, oh, I have to call this constraint method, of course. So for all the points, let's just do this constraint after the update. So for all the points, we bounce all the points against the walls or against the canvas. And for all the points, we constrain those points inside the canvas. So save it. Let's run this one. Beautiful. So you see, as we reach screen height, we flip the velocity and it goes up. Let me just show you one more thing. If I come here and not only kind of this pseudo-gravity thing, if I say 100 to the right, I have the correct integration moving to the right and then bouncing left, bouncing right. This is us simulating movement using the Euler Integration method. All right? I want you to pay attention. Do you see how our balls are right here? Let's just run this for a while. You will see that the height that the balls achieve is going to grow and grow more and more. Why is that the case? Well, you will see that people say that this Euler integration method right here, the way that we implement it, it is going to be an integrator that makes the system gain energy. Do you see how the height of the balls are getting taller and taller, right? The balls are actually gaining energy, right? They are not decreasing the height. They are going to eventually, they're going to almost touch the top part of the canvas right here. You see, they're going more, and as they bounce, the system is gaining energy. Why is that? Well, the way that this integrator method works, this explicit Euler right here, is if you look at the graph, this is what happens to the particle. As time passes, the energy of the system is getting bigger and bigger and bigger. This is a numerical property of this integrator method. So in our case, as our particles started in the middle of the screen, you see how they are now bouncing and even touching the top. Now they gain energy. This is just a numerical property of this integrator, right? Different integrators, different methods, they have different properties. Some of them gain energy, some of them lose energy, some of them are more accurate, some of them are more stable, some of them are more expensive to compute, some of them are cheaper to compute, and we're going to look at some examples right now. So, if we go back here to our Euler method, this Euler method that we just implemented, this is what we call explicit Euler method, and is basically computing the position and then computing the velocity after. And this velocity is going to be used in the next simulation step. But there is a simple hack that we can do to increase a little bit the accuracy of our simulation, which is, instead of doing this thing, position and then calculating the velocity of the next frame, we just flip these things around. And this is what we call semi-implicit Euler method, which is basically almost the same thing, but we compute the velocity of the next frame first, and then we use the velocity of the next frame to compute the position of the next simulation steps. Do you see? It's just a change in the order that we do things. Look at this case. Now we compute this dot velocity first using the integration of the acceleration. So we compute the velocity of the next frame, and we use this velocity updated that would be for the next frame in this computation of the position that we want. So it's almost like we're trying to get ahead of the curve, right? We update the velocity, and we use the velocity of the next time step in the update of this position. This helps with the accuracy. Do you see how our curve now fits a little bit better the exact solution? This is just a trick that we use. If you have to use Euler integration, please use semi-implicit Euler method in your simulations, right? Which is basically just saying that by changing the order and saying that this dot velocity gets updated before the position, we end up getting more accuracy because we're trying to just look and peek and stay ahead of the curve in our prediction. So just by changing the order, now making the velocity being updated before and using this next velocity to update the position right now, we get a little bit better accuracy. And you will see that our system is not going to gain energy. The accuracy of the movement is going to be a lot better, a lot closer to that exact constant acceleration continuous function that we have. But the system does not gain energy. Actually, you will see that the system slowly loses energy. So eventually these balls, these particles are going to go and start falling and falling and falling and getting closer to the floor. Right? This is a property of this semi-implicit Euler integration method. And if you look at the graph, the same way I had before, the semi-implicit Euler method is going to lose energy as time passes, but is a lot more accurate than that explicit Euler method that we had before. Gustavo, why are we talking about integration methods so much and we haven't even touched Verlet integration? Well, the reason why I'm showing Euler method first is because it helps us put things into context, right? Understanding what a numerical integrator is, what it's trying to achieve with this estimation, these predictions of what is going to happen in the next frame. Thinking about accuracy of methods, right? We have the implicit Euler method, we have the explicit Euler method before. Before we get to Verlet, let's start with the question, right? So how can we get even more perfect fitting of that function? Can we increase the accuracy of our methods? And that is a valid question that people have been asking for several years. Verlet integration, Euler integration, they are not the only ones. For example, let me just show you one example of what I'm talking about. We have something called, for example, the midpoint method, which tries to be even more accurate in the estimations. And how do we do that? Look, I'm not going to go into too much detail and explain exactly what the midpoint method is, but I want us to have a gut feeling and an intuition of how this works. So in the midpoint method, let's say that we have a curve, and I'm going to zoom in into one time interval. Do you see t of n, and then we have that delta time, the difference of time, and then we have t of n plus 1, right, the next moment in time. This right here is our delta time. I'm just zooming in into one time interval. The way that we do things is, the difference between what we used to do with Euler before is, so in the Euler method, we used to go and we used to look at the slope and estimate. But instead of going entire delta time, in the midpoint method, I'm going to go only in the middle, so delta time divided by 2. I just go to the middle, and right here, I'm going to go and sample again the velocity, the slope of that function. And by looking at that slope, let's just say that right here, the slope is like this, right? So this slope right here, this new slope here in the middle that we just sample, we're going to use this new slope for the prediction of the next one. So we use that slope as the new prediction from xn to find the xn plus 1. Do you see what we're doing here? We're trying to kind of compute a little bit more. Instead of looking at the entire delta time, we're going to go and divide, find this midpoint of this kind of previous Euler method. We find just the midpoint, and then we sample again in the function what is the slope, and we use that new slope as the prediction. Again, I'm not trying to give a formal explanation and very rigorous explanation, but this is what we have. If we want to look at the formula, it's kind of something like this. It's a little bit scary, but it makes sense, right? So the next position in time, xn plus 1, is the current position in time plus, and then we have to look at the function, look at this f as this function, right? As this kind of position to time of xn plus half delta time. You see midpoint, because we look at the half of the delta time velocity, tn plus half, so tn plus half is tn plus half of delta time, midpoint. And then multiply scale by delta time again. Again, I don't want us, this is not a video about the midpoint method algorithm. I just want us to have a gut feeling of how people try to improve the accuracy of the methods, and the midpoint method is one of them. We can go even further, right? So there is something, I just want to mention again, there is something called, you probably heard out there, called the Rangakatta order 4 method, right? Or RK4 method. And the RK4 is, it takes everything that we just learned and takes us one step ahead. So do you see how the Rangakatta, however you want to call it, right? These German creators of the method. The Rangakatta is very, very precise. It's very, very accurate. But it has the problem of being more expensive computationally to compute things. So the Rangakatta method does kind of exactly the same thing, but it takes things to the extreme. Instead of just looking at the midpoint, it does these things 4 times. So it goes, it finds this first estimation, samples the velocity, looks at the slope. This slope goes until the middle again, and then we sample again and we look at the slope, and then we look again, and then after 4 times doing all these shenanigans, we go and we estimate again, and then we find something that produces super accurate estimations. Again, I don't want us to go too deep, and I'm not trying to rigorously explain the Rangakatta method, but these right here are the formulas. So we're going to have 4 helper variables. There are going to be all these different vectors with different slopes. So k1, k2, k3, and k4, they are this, they go until the middle, find the slope again. After the slope, I go back and I estimate, find to the middle again, and then I estimate all these 4 times. This is why Rangakatta is what we call an order 4 integrator method, right? RK4, order 4, because of these 4 steps of computation, these 4 samples that we have to do with the function. And at the end, this is kind of the formula, right? It looks scary again, but think about this. The next position in time, xn plus 1, is the xn that I am right now, plus. And then I use all those k1, k2, k3, and k4. I use a little bit of k1, I use 2 times, a little bit more of k2, a little bit more of k3, and then a little bit less of k4. So I have these weights. 1 plus 2 plus 2 plus 1 is 6, and then I just divide everything by 6 to average everything out, and then, of course, scale by delta time to integrate that thing. This is a very, very high-level overview of the RK4, which you probably heard out there. So the question is, Gustavo, if RK4 is so accurate, why are we not just going and using all the time RK4? Because we are talking about game development, we are talking about game programming. We don't have all the time in the world, we don't have processing power, we don't have memory, so doing all these 4 times, right, all these extra computations is usually a deal breaker for most real-time game applications. So if we look at this kind of table that we have, if you think about Euler, if you think about Rangakatta, Midpoint, the expense, right, the cost of computing these things grows as we go from left to right. So the Euler method is super, super cheap to compute, meaning that it is extremely fast. And fast is what we need with game development, right? I don't worry too much about accuracy, but what I need is speed. I need things to be computed super fast because I'm doing this frame per frame of a game that has several other things happening at the same time per frame. And if you want more accuracy, then you can use the midpoint method. If you want even more accuracy, you can use RK4, and there are even more fancy methods out there. So if you want to estimate and predict the trajectory of an object in space, maybe you want more accuracy. But since we're talking about games, we don't need accuracy most of the time. If you took our course at picuma.com where we create this physics simulation from scratch, you will see that I use Euler integration in our physics engine, and it is good enough. It gives us some good enough approximations of movement. And that is what we want in a physics simulation that is targeting games, right? Specifically game programming. So, Gustavo, what about Verlet integration, right? Why is Verlet integration so popular in game development? Mostly because Verlet integration is also accurate enough, is also super fast, but there is a property of Verlet integration which is numerical stability. And this is especially important whenever we have a system of several points and several particles connected and constrained with each other. Whenever we have particles connected to each other, where the movement of this particle depends on the movement of the other one, and this other one depends on the movement of this one, we have all this constraint connecting the points together. This is where Verlet integration excels. Right? These ideas of having all these constraints constraining the movement of objects, multiple objects together. So why is Verlet integration different, and how do we achieve this numerical stability? Verlet integration was first used in 1791, and it was used by this guy called John Delambre, but it was rediscovered and discovered again and discovered again many times in history, right? So most recently, you will see that someone called Luc Verlet in 1960s used these things to estimate these ideas of subparticle trajectories. So Verlet integration is not just used in game programming. There are several applications. For example, P.H. Cowell and A.C. Crummelin, they used Verlet integration to compute the orbit of Halley's Comet. It gives us this accurate enough approximations. It provides good numerical stability and also time reversibility. So the Verlet integration, it helps us, if we have to go forward in time, it helps us also to go back in time, and it preserves these ideas, right? It is reversible. In some cases, we do want that. So numerical stability and time reversibility, they are the two areas where Verlet really excels. And how does Verlet does that? And right here is one of the most important parts of our video. So instead of storing the position and the velocity, which we did with Euler, for example, right? We use the position and the velocity. We don't store the velocity anymore. Verlet integration stores the current position and the old position. So we do not store the velocity of that object. We are only dealing with current position and old position. This is why we also achieve numerical stability. We don't lose lockstep between position and velocity. Given the current position and the previous position, we always try to keep things stable. So by having the current position and the old position, this is what Verlet tries to accomplish. Because, look, the velocity that we are going to use to estimate the new position is given by the two positions that I have. So the old position and the new position, this difference right here is what implicitly gives us the velocity that we're going to apply to find the new position. Right? So the bigger the distance between the old and the new position, you can think of it as bigger velocity, right? So, and the shorter the distance, the slower our particle is moving in time. So how do we get to this Verlet integration in the first place? I want to start by, let's go back to that semi-implicit Euler. Do you agree that these two formulas that I have right here, Vn plus 1 is Vn plus A delta t, and then Xn plus 1 is Xn plus Vn plus 1 delta t. This thing right here is the semi-implicit Euler. Remember, we are using V of n plus 1, so we are trying to look at this new velocity, new updated velocity of the next moment in time, and we use this new velocity to find the new position. This is Euler integration, semi-implicit Euler integration. And I'm going to start by, do you see this formula right here? The next position in time is equal to the position xn plus the Vn plus 1 delta t. I am going to force, and I'm going to move everything n minus 1. So I'm going to kind of push everything one moment in time before. So if I subtract n minus 1 out of everything, the equality holds true. And this is what I have, right? So this thing right here, subtracted n minus 1, is going to be xn plus 1 minus 1 is going to be xn equals to xn and then xn minus 1, so I just subtract minus 1, and also, right, velocity n plus 1 is just the current velocity Vn delta t. So all I did was I subtracted minus 1 of all the n's. So I kind of just rewinded a little bit, right, one step before. Now that I kind of subtracted minus 1, I am going to, let me just find everything in terms of velocity, right? So what is our velocity at this current time? Well, if I just do some simple algebra, right, if I just isolate v on the left, so v, the current velocity, is the xn minus, right, if I just subtract everything by xn minus 1, so xn minus xn minus 1, and then since this thing is multiplying, I have to just divide everything by delta t. Simple algebra, I hope that everything makes sense, right? So Vn is this thing right here. I want us to pause right now, and I want us to look at this formula right here, right? Not just look at the formula and the symbols, let's just try to look beyond the formula. What is this thing telling us? The current velocity is given by the difference between the current position and the old position divided by delta t. Does that make sense for you? The velocity of our system is given by the difference between the current position minus the previous position divided by the delta time, divided by the difference of time, xn minus xn minus 1. The difference between the current position and the old position divided by the interval of time is going to be the velocity, right? The current velocity of our system. All right? I want us to pause right now, and you see this Vn plus 1. Let's just replace this Vn plus 1 with the previous Vn plus 1, right? So everything that I have here on this top formula, I'm going to replace on this Vn plus 1 right here, which is exactly what I'm doing right here. So x, next position in time, is xn plus Vn plus acceleration times delta time, that comes from here, times the delta time before. This formula right here, let me just simplify, so let me just distribute this multiplication, right? Delta times v, delta times this thing, so just distributing is going to be x of the next position in time is the current x of n plus the current velocity times delta t, that I just multiplied, plus the acceleration times delta t squared, which is this thing multiplied here as well. Right, so now we have this vn, this v, right, velocity of the current time. I'm going to replace this Vn by this thing that we have right here that we just calculated. So the velocity right now is the difference between the positions, current and old, divided by delta time. Let's just replace. Same thing, xn plus this thing right here that came from here, divided of all these things. Let's just simplify even more. Do you see? This thing is multiplying, this thing is dividing. I can just cancel these things out. So just canceling delta t with delta t. I end up and I find this formula right here. And this formula is the Verlet integration formula. This is what we're going to use to estimate the new position based on the old position. Because do you agree that we don't have velocity in this formula anymore? All we have is current position and old position. And of course, the acceleration of the system that comes from the application of forces. But we don't have velocity. The velocity is kind of implied by this difference. Do you see x of n minus x n minus 1? These two things right here, this subtraction, is almost like the velocity of our system. But it is implied, and all we store is the current position and the previous position, the old position. This formula right here is the formula for Verlet integration. Actually, let me just pause, and if you open Wikipedia and if you look at the Verlet integration formula, you will see that the formula that they give is x of n plus 1. So the new position is 2xn minus xn minus 1 plus acceleration delta time squared. What is the 2xn that we have there? Well, it's exactly what we have right here. Do you agree? xn plus xn minus xn, that is 2xn. But I just like to leave it like this. I don't like to put that 2xn because this thing makes sense for me, right, intuitively. X of n plus 1 is the old xn, is the current xn, plus the difference between xn and xn minus 1, right, the difference between the current position and the old position, plus acceleration delta time squared. So that 2xn, you can, if you want to use that, of course, but it's the same thing, right? 2xn is exactly the same as xn plus xn minus 1. Does that make sense? This is Verlet integration. So we are not going to store velocity anymore. All we store is position and old position. That is all we need to store in our particles, in our points. We're only going to deal with these two positions. And by storing only positions and not having this difference between velocity and having to create this lockstep between velocity and position, only using position, it creates more numerical stability for us in our system. All right, so let's go ahead and implement this thing right here. Let's come here and let's change this Euler integration to use Verlet integration. And the first thing I want to do is, do you remember how our point was storing the velocity x and y besides the position? That is not what we're going to do anymore. I'm going to replace this by having the current position x and y and the old position x and y. This is what we're going to store for this particle, for this object. X and y position and the old x and y position, besides the mass, of course. I'm just choosing to initialize the old position as the current position whenever we are creating our particles, our objects, right? This is not going to be Euler integration anymore, so we're going to use Verlet integration in our update. And you know what? Do you remember how our constraint was using the velocity and flipping the velocity? I am not going to use this anymore. We're going to have to rethink the way that we change the bouncing of the walls. So we're going to have to think about this very soon. Rendering is still the same. Creating the points is still the same. I just create 2 points at this x and y position. X and y position, I don't have velocity anymore in the constructor. And I think that's it. So right now, we don't have anything in the update. We have to use Verlet integration. How are we going to use Verlet integration? Well, the first thing I'm going to do is I'm going to leave the formula for Verlet integration at the bottom, right, at the right bottom of our screen, so we can look there and remember what Verlet integration is all about. That formula, do you see how we have that term xn minus 1? That difference between the current position and the old position, that is our velocity in a way, right? So I'm going to have these two velocities, velocity x and velocity y, which comes from the current position, this dot x, minus the old position. So the velocity is given by the difference between positions, current and old. Right, so this is one of the things that we have to do with Verlet integration. The next thing I'm going to do is I am going to already save in the old position the current position. Right, so I'm always storing back the current position becomes the old one, the current y position becomes the old y. Right, so now that I have the velocity x, velocity y, and I update and save the old position as the current one, I am going to also compute the acceleration of the system. Remember how acceleration came from the force divided by the mass? That still holds true. So I compute the acceleration using F equals ma, but then A equals the force divided by the mass. The bigger the mass, the less we accelerate. The smaller the mass, the less we divide, the more we accelerate, right? Inversely proportional relationship between the acceleration and the mass of my particle. So force divided by the mass, force y divided by the mass. And now that I have the acceleration, I have pretty much everything I need to apply that formula that we have there on the bottom. So what is our next position n plus 1 in time? There we go. We're going to estimate the new position using Verlet integration. This dot x, so the next position in time, is plus equal, so it is the old position plus velocity of x, which is that difference between current and old position. So it is the velocity of x plus the acceleration times delta times squared. And the y, the same thing. Velocity y plus the acceleration y times delta time squared. Exactly the formula that we see there on the bottom right of our screen. Verlet integration formula, right? This is our numerical integration method. And I think this is all we need to see an actual movement, to see our acceleration taking place. So if I play, we see beautiful. Let's just quickly think about this constraint right here. Because look, bouncing off the walls is not going to be as simple as before, because we have this weird thing going on, right? In the Verlet method, right, given that we have the ball, these points, and the wall, the Verlet method, we do not have stored the velocity. The velocity is given by the difference between the current position and that old position. And then we calculate that difference, and that will give us this kind of velocity-ish type of thing, and then we predict that the new position is here. New position, old position, the difference kind of gives us this kind of velocity effect, and then we end up here. But the thing is, if I go and I use that, what we were using before, remember the projection method that we just forced this thing to be right on the wall? This is going to break our logic, because we are effectively changing the position. And by changing the position, do you see how the difference between the current and the old is a lot shorter, and even the direction change? So we are messing up that velocity, right? We enter the collision with one velocity, and now we are kind of changing everything. This difference, I cannot just change these positions as I want. For me to conserve these things as they were, I'm going to have to, the velocity is always given by the current position and the old position. So I'm going to have to change things. I'm going to have to set the old position correctly right about here, right? Because to maintain that distance. So that distance is x. So what I'm going to do right here is I'm going to cheat a little bit, and I'm going to say that I'm going to change the old position to be right about here. So I'm going to move it to be right about here to maintain that difference, right, between the current and the old. So it's going to be, I'm going to add the velocity thing in x. So the old x, I'm going to change the old position to be the previous x plus the x component of the velocity. And that is going to put our projection right here. this thing right here is kind of keeping, right? Keeping that distance that I had before. Again, it's not perfect, but it's just a hack that I think is going to work okay for us. And now, do you see? This distance right here is going to give us that velocity, which is similar to that distance that I had before. And then we can just continue and start simulating again, right? So given that I changed the old position to be right here, that is keeping that difference between old and current position, because that is what is going to give us our velocity, and that is how we predict and estimate the new positions of our system. Right, so this is a little bit of a hack. You see, it's very dirty. It's not perfect, but I think this is going to be okay for now. So we just have to kind of add the x component, and if it is in y, the same thing. So in our constraint method, I'm going to first, I need to compute the velocity, which is given by the difference between current and old positions, x and y. And right here, I'm going to test if I collided with the walls. And let's say, if I collided with the walls, right, so if this is less than 0, I'm going to say that I'm going to do the projection method, force it to be on 0, and then the old x position, I'm going to force it to be the current x plus the x component of velocity, because the velocity in this case is negative, right? If the x is hitting the right side of the canvas, I do that thing. I say the x is equal to the screen width using the projection method, and then this dot old x, so the old position now has to be the current position plus the x component of the velocity, as we just saw. And the same thing with the y component, right? If I hit the top part, I force it to be 0, and then the old y, I just add to the velocity, which is negative. And if I reach the bottom of my canvas, I force it to be on the exact bottom of the screen, and then the old position y, I have to change the position y to account for this plus velocity, because by changing the old positions is how I get this correct velocity of my system, right? Remember, the velocity is given by the difference between the current position and the old position. So I'm changing the old position to correctly account for this bounce. Let me just see if this kind of does what I want. Just bounce. Yeah, so as we reach there, we just change the position. I think the bounce is okay. Again, it's not perfect, it's just a hack that I think is going to work for now. So everyone, this is Verlet integration working in our system, right? All these lines of code right here in our update, they are using that formula that you saw before, that we derived, right? Using only the current position and the old position, and of course the acceleration of the system given by the forces. Only using these two positions, current and old, we can create this simulation of movement of our system. Verlet integration is accurate enough, it has a similar accuracy as the Euler integration, but it is more numerically stable. And the reason why we say it's more numerically stable is mostly because we work with Verlet integration in the system of multiple particles connected to each other and applying forces against each other. So whenever you have this system of several particles and several constraints and springs and sticks connecting all these particles and all these objects, whenever you have all these constraints playing together, Euler integration tends to break faster than Verlet, right? And Verlet is a lot more numerically stable. That is why Verlet integration is so popular. All these examples of games that you see using these points and springs and points and sticks connecting these points and particles, this is very popular, very traditional Verlet integration. So, Gustavo, what about these constraints, right? What about all this connection between the points? Because let's face it, right? Whenever you hear about Verlet integration, this is what you imagine. All these points, multiple points connected by these constraints, these springs, these sticks. So let's just speak about this very quickly, and let's just see if we can implement this as well in our toy project here. So our constraints, in our case, I am going to call them sticks. And the reason why I'm calling them sticks is we're going to create these sticks between the points. And it doesn't matter what happens in our simulation. It doesn't matter if the gravity is pulling, if there is wind blowing. We need to maintain the distance between, let's say, PA and PB always a length of 100. And also, we have a stick between PB and PC, right? These 2 points. We need to maintain always a distance of 100. It doesn't matter what happens in our simulation, we need to enforce these constraints. And I'm calling it sticks because it is always a static, right? It's always constant 100. There is no springiness, there is no soft body movement. Everything is just sticks. It's just a constant value of 100. We need to maintain that distance. And it is no surprise that we're going to have a new stick object, right? We're going to have a class stick. And a stick is always between 2 points, P0 and P1. And we always need to establish a length, right? So we initialize P0, P0, P1, and a length. And we can have an array of sticks that we start connecting these points, right? So I can say that I have my first stick is between 0.0 and 0.1 and is 100 length. 0.1, the next stick is going to be between 0.1 and 0.2, 100, 0.2 and 0.3. So it's always between the first and the second and the third and the fourth, and then back to the first, right? So and also between the first and the third right here, right? Because I need to kind of create this, I need to strengthen the core of our stick, right? I need to create this kind of box, this rigid kind of box, just by connecting sticks together. All right, so these are sticks. If you just want to come here quickly and implement this. So now, besides having a class point, I'm going to have a class stick right here at the bottom, which I am going to have P0 and P1, and the length, I initialize my attributes here inside, and then I'm going to have an update which has to maintain that constraint. We need to enforce that length distance. And I'm just rendering with a line, so I just go from P0x to P1 x and y. I just create a little line between the 2 points. That is going to be the visual feedback that we're going to have for our sticks. Let's just create 2 points here. Let's just say 250, 100 height, and 450, 200. So I'm going to have still 2 points, those 2 particles, and I'm going to have an array of sticks where I only have 1 stick. So it's going to be 1 stick connecting points of 0 and points of 1. So the first and the second points. What is the length that I want to enforce? Well, I could just say 100, right? This constant 100. Or you know what? Instead of just writing this thing manually, let's just compute dynamically the distance. So distance between 0.0 and 0.1. And this distance function is a distance between 2 points. And I don't think I need to explain that much this function. I think we are tired of implementing this. The distance between P0 and P1, these 2 points, is going to be the difference in x and the difference in y, and then we use the Pythagoras theorem, right? We find the hypotenuse of that triangle, which is the square root of the distance of x squared plus the distance of y squared. Look at that image on the right and see if this makes sense. We have 0.0 and 0.1. We find the difference between x's and y's, the sides of that right triangle, and then to find the hypotenuse, which is the actual distance between them, I just compute the Pythagoras theorem to find the hypotenuse, square root of the 2 sides of the triangle squared and added together. Right, so this is the distance between 2 points, just simply using the Pythagoras theorem. I think this is pretty common. And then I just use this to dynamically compute the distance between those 2 points. Very well. So I just think I need to come down here and render also all the sticks. Let's actually render the sticks before the points. So the points are always drawn on top of the sticks. So for all the sticks, I just render all my sticks. Correct? And right here, do you see how we are updating all the points and then we are bouncing off the walls? I want to come here and update all my sticks as well, right? So we have a new iteration. So for all the sticks, we want to update stick.update delta time, because this thing right here is what is going to enforce that distance. We have to change the position of things to enforce that we are always, let's say, 100 pixels between point A and point B, or point B and point C, and etc. So we are going to have this update, but of course, it's still to do, right? We don't have anything. I think if I play this, we're going to have the stick, but of course, there is no constraint being forced. So it is just a stick that is not really a stick, it's just a line connecting those dots. We need to now think about enforcing that constraint, enforcing that the stick is always a certain distance. We need to keep that distance between the 2 points. Let's think about that. We're going to start with a couple of facts. We know that we have 2 points, P0 and P1, and we have this stick constraint that is connecting those 2 points, and we are setting it to be always 100. So we need to maintain a distance of 100 pixels between P0 and P1. Doesn't matter what happens. If they are falling, if the wind is blowing, if there is friction, we need to always maintain and push things or get them close together. We need to update the position to always enforce that there is a distance of a length 100 between 2 points. That's it. So if by any chance our simulation is happening, there is wind blowing, and we end up in this case right here, where let's say that they kind of stretch, right? P0 goes that way, P1 goes this way. So let's just say that we end up with a distance of 140 between point 0 and point 1. If we have a distance, right, after our simulation updates the points, and our points are now 140 pixels apart, we are going to have to go, and our update stick is going to have to push things, right? So we're going to have to apply, if it was 140, to get back to 100, I have to push. We have to divide the changes, right? I cannot just push one. I have to push both. So I have to divide. This one goes minus 20, that one goes plus 20, and we restore our position. And the other thing also, right? If we have the same situation, but now something compresses our points and they are closer to each other. So let's just say now, after the objects are applied gravity, we have the weight force, or there is friction, there is wind blowing. If they are closer than they should, now let's say 80, we need to get back to 100. So I have to calculate, find the percentage of change, and these things need to, let's say, I need to apply 10 here and minus 10 there to get back to 100. Do you see how we are going to approach this? So this is the easy solution, because we need to think about a little bit different if we're talking about 2 dimensions, right? Let's say that we have these 2 points, P0 and P1. And if this length stays always 100 pixels, what happens if we have, let's say, these 2 points? This one goes to the left, this one goes to the right. Now I end up with a distance of 120. They are 120 pixels apart. I need to find what is the delta x and delta y. What is the offset in x and y that I need to apply to these points? I'm going to cut to the chase and show how I think about this, right? The way that I'm going to find this is by breaking things apart into x and y, right? I need to break things into x component and y component. How much do I offset this object in x and in y to get back to 100, and that one also x and y? So I'm going to think about, I need to change these things 10 and 10, right? That is the hypotenuse of the change. So I'm going to have a dx and a dy, right? So the difference in y between the points and the difference in x between the points. I need to find how much the offset delta x that I need to apply and the offset delta y that I need to apply to that point, and also that one, right? So plus delta x plus delta y minus delta x minus delta y for one and the other. How do I calculate and find this offset delta x and delta y? The way that I'm going to do that is by using this formula right here, right? So don't worry, it's nothing too scary. If you break things apart if you break all the lines, you understand exactly what we're doing. I find the dx and dy. Of course, dx and dy are going to be the difference between the x's of point 1 and point 0, right? So p1x minus p0x, that is going to give me the dx, and the dy, which is this difference right here, this side of the triangle, is going to be the difference between p1y minus p0y, right? So p1y minus p0y is going to give me the dy. Now that I have dx and dy, I am going to find the distance between those dx's and dy's, right? So if I have the distance, right, to find this distance between those 2 points is going to be the square root of dx times dx plus dy times dy. That is going to give me that distance, right? The total distance, which is, in this case, this 120 pixels apart, that our objects, our particles that are broken, the constraint is broken, so the distance between them is currently 120. What is the difference? Well, it is 100, which is the length that I need to enforce, 100 minus the distance. That is going to give me the distance that they are from the optimal solution, which is 100. This difference, I'm going to find the percentage that I need to apply for both of the objects. So the percentage is the difference divided by that 120 total distance, and then this percentage I have to divide by 2 because I need to kind of break things into those two objects, right? I need to offset A and B, 0 and 1. So I need to divide by 2 to get this percentage that I need to apply to both objects. So the difference that they have by the distance, which is that current distance, 120. So the difference, current divided by the distance, divided by 2. So I kind of divide things into two objects. Then I just let my offset x is the dx times the percentage that I need to apply to A and the percentage that I need to apply in y. So percentage in x and percentage in y. I then go and I offset the original P0 x and y minus that offset x and y that I just calculated. So I do minus to P0 and plus to P1, right? So P0 x and y minus that offset that I just calculated with the percentage, and P1 x and y plus the offset that I just calculated. So left and right, I just push them apart. Delta x and delta y, delta x and delta y. Offset x and y. Does that make sense? So this is the logic that I'm using. I'm just finding that delta x and delta y by using these differences, finding the percentage, dividing things by 2 because I need to find the percentage for one and for the other, and then I apply that percentage in both x and y as this offset x and offset y minus offset x and offset y plus, right? To get minus plus P0, minus P0, and P1. And this offset x and y and this percentage and this difference, they can all be positive and negative, and they are going to work accordingly as we want. If things are going left, things are going right, the value of this offset is going to be positive or negative, so we're going to add or subtract correctly. Very well, so let's just get this function, copy and paste in our solution. So right here in our stick class, whenever we are trying to update each stick, we are effectively calculating how much they are apart, and we are changing the position of points 0 and 1, those 2 points that are connected by the stick. I change the x and y, minus and plus that offset x and y, always changing their position to keep that constraint, to enforce that the length is always 100, or whatever is the distance that we are initializing. Very well, and if I play, I'm going to have these two sticks. You see, it always maintains the difference. This is us implementing a hard constraint. We are just going and changing the position directly. Let me just change this thing. I don't want any force x. There is no wind, no friction, nothing. So it's just falling down. That looks pretty good to me. Very well. So let's just kick this up a notch. Super simple. Let me just stop and let's just add more points and more sticks. So if I come here, whenever we are creating our points and sticks, now I'm going to have not just 2 points, I'm going to have 4 points. So A, B, C, and D at these x and y positions. They are all mass 1.0, right? I just don't want to give different masses for now. I could if I wanted, but let's just leave 1.0. And not just points, we're going to have an array of sticks connecting point 0 and point 1, point 1 and point 2, point 2 and point 3 back to the first one, and also point 0 and point 2 to get this diagonal right here. So I'm connecting A with B, B with C, C with D, D back to A, and then A with C, just to keep this rigor here so they don't break, and I don't need these sticks no more. Is that it? There we go. So you have things rotating. That looks pretty cool, right? So this is us implementing constraint, and we're still using Verlet integration, right? The core of our movement system, our integrator, is based on Verlet integration. And you know what? Let me just go ahead and do something super cool, which is we could come here and say that our points, some points in our system could be static, so they could not move. It's almost like we go and we put a pin in it. So I can just say it's like a Boolean pinned. and this dot pinned equals pinned. Right? So I can just say that. Let's just change our pins. Let me change our points. Let me just copy and paste here. I want to have now 4 points plus an anchor point. And this anchor point is the only one which is pinned true. Right? Everything else is pinned false. I actually didn't have to pass this parameter, but anyway, this one, the last one, is the only one which is true. I'm calling it the anchor point at this position, 400, 100, at the top of the canvas. And then I'm going to have a new stick, which is going to be like this. I'm still connecting those points A, B, C, D, but now I have this final connection, which is the anchor point, the one that is pinned, I'm going to connect with the point C. This thing right here, since the anchor is pinned, I don't want to ever move this anchor. So the way that I'm going to do that is, I'm going to look in the update method of the points, and I'm only going to update and only going to change and process everything if this is not pinned. So if it is not pinned, I do everything I need to do. Otherwise, I actually go and I process this thing. So this update is only going to happen if my point is not pinned. And you know what? In my stick constraint, I am only going to offset x and y if this dot p0 dot pinned. So if it is not pinned, so if the p0 is not pinned, then I go and I offset, and same thing. Only if my p1 is not pinned, then I offset. Only if it is not pinned. Correct? So this offset of the stick and this update of the points only happens if our points are not pinned. Look at that. So everyone, if you got this far in our video, can you just write hallelujah in the comments? Because this is super cool, right? This is the foundation of something that you can just expand and create something incredibly fun, right? You can have a lot more points. You can programmatically create more points, or you can create a mesh of points and all these sticks connected together. This is the basis of something you probably saw out there, cloth simulator, right? So if you have this 2D cloth or 3D cloth, you can use Verlet integration with all these particles, these points and sticks connecting each other with all these constraints, constraining the motion of the dots of the cloth. And then you can move them around, you can apply forces. So cloth simulation is a classic example of Verlet integration in action. You can have maybe a wheel rotating, you can have these objects falling, breaking the constraint. So the sky is the limit from here onwards. You have examples of games that use Verlet integration. There is a game from Johan Pates, which I think is amazing, is super creative, where you can go and with the mouse, you can go and click and create these pin points or create this constraint between the points. And then you can create the levels that you have to go and create bridges, and you can go and move with these little characters around. It is a super fun game. I think it is amazing. You know, these people are actual game programmers, right? I'm not a game developer anymore. I don't even play games anymore, but you have these actual game designers, game programmers doing amazing things. And the heart of the mechanics of their physics simulation is based on Verlet integration, right? So I thought it was important for me to mention all these ideas of cloth simulation, all the systems that connect many points with many constraints. The reason why we use Verlet is because of numerical stability. And as you can see, the implementation of Verlet is nothing difficult. We can just implement super simple. The core idea is what you see right here. This is Verlet integration in action. And some people say, okay, Gustavo, so if Verlet integration is so cool, why didn't you use Verlet integration whenever you are teaching how to create a physics simulation? Look, if I could use Verlet integration, it should be okay. It is a numerical integrator like everything else. It has good accuracy, good stability. But in my case, I went with Euler integration, right? The semi-implicit Euler integration method. It was accurate enough, it was good enough for what we needed, and our physics engine that we implement in our course from scratch, we use rigid bodies, right? And rigid bodies, collision, we have to detect collision. So most of the time, most of the physics engines that I've seen out there, they still use Euler integration methods. There's nothing wrong with it, right? It's just a different one. It's just a trade-off between speed, between memory use, between accurate estimations and predictions. Everything is basically a trade-off. We have to pick. In our case, for game programmers, especially in the realm of retro programming, right, these old machines and MS-DOS games and PlayStation games where we didn't have computational power, Verlet is very popular, but also Euler integration because we need speed, right? I don't need that much accuracy, but I need speed. I cannot sacrifice FPS just to get a little bit more accuracy of our physics simulation. All right? So look, I had a lot of fun. I love this topic. I can speak about physics simulation and numerical integration, mixing this mathematics with programming. I love this topic, right? If you like this type of content, remember, at picuma.com, that is where I actually teach. We have comprehensive, focused courses that teach mathematics, computer science, physics simulations, game engines, all this cool stuff. All right? That is Verlet integration, physics simulation. This is a super cool topic. Hopefully, I will see you also in my next videos. Ciao, ciao.